if I start the lecture and you don't see it's announced as recording, someone holler at me and tell me what you put on the recording. In regard to the recording of the last lecture, it's on my drive set, but you don't all have access to that. If you want to see that lecture, the recording, please send me an email, pizer@cs.unc.edu, and I will make sure you have access. However, one of the LAs is in the process of moving that recording and all others onto the, I guess it's called Panopto capability that comes with Sakai. And from then on, you'll be able to access it through Sakai, and therefore there won't be this problem.
Hey, Professor, it's already on Panopto, so it should be accessible now.
Perfect. Thank you, Andrew. Okay, so this lecture and all others, whether they're offered remotely or in person, can be found on Panopto. Secondly, I guess you all know that I am. I just passed my 80th birthday, and a little bit sensitive to. Although my health is very good, I'm a little sensitive to being more than a little sensitive to being infected by the COVID-19 virus. At the moment, my present intention is, beginning next Tuesday, to be giving the class in person. But if you're following the news, you may notice that what's happening with this Omicron virus is it's having a very, very high, sharp peak, but a very, very sharp fall in at least in the places that started it early. I expect that to happen here in Chapel Hill as well. And I'm going to be following both what the university is deciding as a whole and what the reports of the incidents of these infections here in Chapel Hill are. Hold on, I need to. Okay. Okay. So what I'm saying is that I expect I am certainly going to start in-person classes soon, and my intention is to start that on Tuesday. But because I want to monitor things, I am going to monitor things over the weekend. By Monday noon, you all should have received an email from me, explicit email saying either we will be meeting remotely on Tuesday or we will be meeting in class. As I said, my intention's in class, but I don't come until you receive such an email. If by noon on Monday you have not received an email, please email me and say I haven't. What's happening? And I will let you know. Any questions on that? Okay. The LAs and I had a wonderful production meeting and set up all the rooms so that hopefully things will go well in terms of my presenting in the classroom, but the lecture being recorded in such a way that you'll be able to see copies of it. And even if people are absolutely need to be remote, they can listen to it online. I encourage you again to ask questions, especially aggressively during these remote sessions, because it's easy to just sit and not ask when I don't even have eye contact with you. Okay, one other announcement. I believe there was a typo on the information sheet that said that my Friday office hours were started at 2:30, and that's not the case. It's 3:30. I will fix that in that document. But if any of you want to meet with me tomorrow for office hours, that will be happening remotely at this Zoom site, starting at 3:30. Any other matters that people want to ask about before we get started? Okay, the Piazza site for the class has been established. I have information from Piazza that only on the order of a third of you have signed up for it. You should go ahead and sign up for it. There will be announcements, official announcement made via the announcements field in Sakai with an associated email to everybody who's on Sakai. But you should also be able to receive information from each other, at least on Piazza. Any other questions? Any other matters that we should discuss before we get into substance? If not, let me screen share. I was going over, what's happening here? Yeah, I was going over the subject material of the course, and I want to complete that now. We talked about that we were going to be talking about local representation of images at a base point via Taylor series, and that was the major topic there was actually going to be the computation of spatial derivatives of images. And then I talked about the fact that there were many operators on images that map images to images and that are invariant to shift. And after defining that, I will spend a lot of time noting that these shift invariant linear operators can be understood best by understanding images to be decomposed or composed of a weighted sum of orthogonal basis images. Okay, so you have these basis images. It turns out they're made from sinusoids, sines and cosines of x and y, or in three dimensions, x, y, and z. And we will talk about these orthogonal basis images and how you represent images in terms of them. And then we will talk about the operation understood as convolution with a kernel, which is another image, since an operator-based related image. Different operators have different kernels. And I said we would talk about image properties of resolution and noise and distortion, and also about what is the effect of discrete sampling, which is how images are done in computers. Going on to stuff that I haven't yet talked about, the course will, after that, continue on to the notion of spatial scale. There are sort of two aspects of that we will learn. One is essentially what level of fineness of the information in the image or the objects in the image we're concerned with. So, for example, Lena's face is at relatively a scale, let's say roughly related to the distance from her nose to the side of her face. Or if you want to talk about the full width of her face, her nose, on the other hand, is a much smaller scale. The individual feathers in her hat are yet smaller levels of detail, and so on. But there's also another important way of understanding scale, and that has to do with the fact that every operator, certainly, for example, derivatives, have associated aperture. a region of the image over which the operator is non-negligibly different from zero. We will see that the particular kind of aperture that's appropriate to talk about has the shape of Gaussian. That is to say, it's a weighting function that is highest in the middle of the aperture and falls off in distance, with distance from the center of the aperture. The size of these apertures is another aspect of spatial scale, and we'll see that these are independent, but on the other hand, that it's a good practice to algorithmically make one related to the other. So when you're looking at large level of detail, that's say big things, you want to use big apertures, and when you want to look at small things, you should use small apertures. But okay, that topic of spatial scale will certainly take us some time. We'll also be understanding the noise in images. That is, when I say noise, I mean that the individual pixel values of voxel in 3D, that those individual voxel values have a random component. So in the ideal image of Lena, the value at the, say, crown of her hat might be out of, well, let's say out of 10 bits, so would be 0 to 1023. So let's say it's at level 900, and instead of it being 900, it might be 902 or 907 or 896 or what have you, according to some random process, so that the image intensities are variable. We'll see that noise is an essential part of the measuring devices that are cameras, and therefore all of our images will have some level of noise. And then it turns out to be important to understand how this noise is related to these spatial scale issues. Your initial intuition that salt and pepper noise is only small scale turns out to be quite wrong. Okay, we will then talk about the fact that images can be represented at a collection of scales. And we will talk about multi-scale representations of images. And in that framework, we'll be talking about splines, which are polynomial functions made up of fitted together patches. Important functions for producing smooth approximations. We'll be talking about Gaussians and their derivatives as being at multiple scales. We'll talk about Gaussians, which have an envelope over sinusoids, like you see in the lower left pattern. If you look at the envelope, that is to say the sort of the smooth function on top and on the bottom, that's a Gaussian. But within that Gaussian, there is this sinusoidal variation. Those are called Gabor wavelets. And we'll see the importance of them for understanding spatial scale and also for understanding texture of images. We will have seen the importance of orthogonality for computational efficiency. And there's these first group of multi-scale representations are not in terms of orthogonal basis functions, and we would rather they have them. And so there is a very interesting multi-scale decomposition called orthogonal wavelets that is multi-scale and also involves oscillating basis forming basis images, not quite sinusoidal. But anyway, we will talk about all these multi-scale representations. Those are important to us. Going on, any questions so far? going on, we will see that when we take an operator, for example, one that's sensitive to edges, that gives high values at edges, when you apply, for example, the gradient function and take its magnitude, that the magnitude of the gradient operator is an edge, produces edge strengths. And if you produce an image of those edge strengths, it turns out that the places we want to say bound an object are ridges in that edge strength image. Likewise, in finding bars, and edges and bars are going to be very important. We'll see how they are accomplished, but via basically first and second derivatives respectively. And then we'll be talking about what it means to be a ridge and how those are used in finding edges and bars. We'll spend a bit of time, not very long, on interpolation, understanding that because that's shift invariant linear, that can be understood in terms of these orthogonal basis functions. But we will also see that approximation, at least, okay, I use interpolation specifically to mean that the values in the result agree precisely with the values that we're interpolating from. Approximation, a more general category, which means essentially that the values in the result are near the results, but not necessarily exactly equal. And it turns out the spline approximation is a very effective way of producing such approximations. And so is an approach called least squares, and we'll be talking about that as well. Questions on any of these? Okay, I see, I think it was Alicia or Elisa raised her hand. Could you ask your question, please?
You mentioned that agrees with the values we're interpolating from, but what exactly does the interpolation do to an image? I don't think I've heard of that before, at least. Okay,
so let's say you have an image that is 64 by 64 pixels. Okay, so it has 4,096 intensity values at 64 by 64 points in the region of the image. Okay, now let's say you want to produce an image that is 256 by 256. For that, we are going to need 10 to the 16th, sorry, 2 to the 16th, 2 to the 16th values, one at each of the 256 by 256 points. Some of those points will be the original 64 by 64 points. In interpolation, those particular 4,096, 64 by 66, 64 by 64 points within the 256 by 256 array of points will need to be exactly what their value was in the 64 by 64 image. The remainder are supposed to be some kind of a reasonably sensible interpolation that we don't have in the 64 by 64 image. However, in approximation, we will say that the values at those 64 by 64 points among the 256 by 256 should be near their original values in the 64 by 64, but don't necessarily have to be precisely equal. Does that help?
So it's like it applies when you're scaling up images?
Yes.
Okay, thank
you. For example, when we rotate images, let me draw this. Let me put on the camera. Give me a moment. Uh, all right. So here we have one, two, three, four, five, 6, 7, 8 points. Okay, so let's say this is one row of a 64 by 64 image. And at each one of these guys, there is an intensity value. So we might have 17.2 here and 19.4 and 16.2 and so on, okay? So we have intensity values at these pixel positions. Now, when we interpolate and want to produce a what you call scaled up, anyway, a finer sequence of pixels, we'll need, let's say, I went by a factor of, in my example, I went from 64 to 56, which is a value of 4. So we'll need 3 additional pixels here, plus the circle, and 3 more here, and so on into each one. So we'll want to value at each one of the X's and at the O's. Okay, and now in interpolation, the O's will maintain their value in the result of the interpolation. They'll still be 16.2, 11.2 and 19.4 and 16.2. But in an approximation system, we might have 11.0 at this circle and 19.7 at this circle and so on as in this result. However, notice that if I now want to rotate the image, okay, so let's say that when I rotate the image, all these guys turn sideways, right? So now the old values are not in XY anymore. I mean, not in just along rows of X or rows of Y because of the rotation of the image. And as a result, I am going to need new pixels that are horizontal in this new coordinate system. So I'm going to need values along here, along that line. None of those, or almost none of those, will pass through the old pixels. Even if I still stuck with 64 by 64, I need my new positions to be along pure X or pure Y. In this example, I'm just showing pure X. And so I'm going to need to interpolate those values as well. That help?
Yes, thank you.
Is there another question? There was a second person asking the question. Okay. Where am I? All right. So we're going to be talking about means of interpolation and approximation. We'll spend a little bit of time understanding an image as a graph. If you look at this little 3 by 3 array of pixels, so think of those as pixels. Each one of these has a value. We can understand pixels not only in terms of their values, but in terms of their relationship to each other. So this pixel value may be about the same intensity as this one, but it might be very different in intensity from this guy here. We're going to be interested in finding edges of images because we need to be able to find objects. And to find an edge, we can think of that edge. Okay, so we're first of all going to understand this as an algebraic graph. An algebraic graph is something that has nodes. Here, the pixels are going to be the nodes. and edges, connections between the nodes. And we're going to let every pixel have an edge to its neighbors. Let's say to its horizontal neighbors, these two here from this guy, and its vertical neighbors, these two. Okay, so we're going to understand those to form a network of these nodes, the pixels, and their and the connections between adjacent pixels. And then we'll understand that finding an object can be understood as a cut through this network. Okay, a cut through this algebraic graph. It's called a graph cut method. And we will understand an algorithm for producing these kinds of cuts. It could be a very useful, in fact, it is a very useful way of trying to find objects. We will see that we will create two additional nodes, one of which we'll call a source node and one of which we'll call a sink node. And then we'll be talking about flows from the source through the network, and we'll see to the sink, and we'll see that the cut is intended to be something that interrupts this flow. Questions? I see none, so let me go on to the next slide. All right, the final topic area. I don't know why, let me, whoop, that was not what I intended. Let me try again. All right. I already indicated that we're going to be interested in these transformations of images, like rotation, like translation, like uniform scaling. And these are very important operations as we relate one image to another. We try to normalize an image. So for example, because I might take a picture of your face with your face just right, with the vertical axis going from your tip of your chin to your nose. And then I may not be such a wonderful photographer, and I may take another picture of you with the camera a bit tilted. And now I want to be able to recognize you in the tilted image, even though my original reference picture was in the non-tilted image. And so I'm going to have to somehow rotate the tilted image in such a way as to match the untilted image, and then I can check whether it's the same face or not. So I have to do this operation of rotation on the images. And the question is, how computationally do we do that? And there's the first thing one learns is that you can do it by matrix multiplication, and that turns out to be an inferior way of doing it. And there's a better way of doing it via a mathematical operation called quaternions, and we'll learn about those. The other thing is that in images, as I told you last time, things that are distant seem to be closer together than things that are close. And we need to be able to transform this into an orthogonal coordinate system where we're talking about the Euclidean distances, the ordinary distances of centimeters, let's say, so that the things that were closer far away, appear to be closer far away in the image, are now transformed into things that are not, in fact, closer, just because they're farther away. And this involves these so-called perspective transformations. And it turns out that both the perspective transformations and the similarity transformations, which involve rotation, some combination of rotation, translation, and zooming, scaling, those all can be done via something called homogeneous coordinates. It turns out we add a coordinate. So you have not just three dimensions x, y, z, but you get a w coordinate as well. And we'll be talking about these homogeneous coordinates and how these transformations work in homogeneous coordinates. We will then move on. Oh, any questions about these so-called affine transformations? Okay, we'll move on to the situations where the regular spacing of pixels is no longer in effect, that these pixels are spaced in a non-regular situation because which is to say we have a deformed image, the so-called distorted image, and then we may want to undistort it, and that's a deformation operation, and we'll talk about how at least one major method for doing this undistortion, this deformation method called thin plate splines. Okay, so the final topic area of the course is optimization. It turns out, for example, that if you want to find an object of an image, you can think of it probabilistically, and that I want the most probable object given the image. Okay, so let's think of all sorts of possible edges, and over all edges, which we will parameterize by some number of variables, we want to optimize, find the best one of those. That will be the boundary of the object that we're looking for, that we'll take to be. Well, these are then optimizations over many variables, right? We're trying to find if, for example, the boundary is represented by 200 variables, we will have to find the best 200 tuple, the best value for all those variables together, over all possible candidates for boundary. And so we will talk about methods for doing these optimizations over many variables that are gradient based. We'll be talking about one called gradient descent or ascent, and a modified or improved version of that called conjugate gradient descent. And then we have situations where some of the relationships are constrained. So, for example, we may be looking for ellipses in a 2D image. And an ellipse is not any old, a boundary of an ellipse is not any old boundary. It has specific mathematical relations that say that it is an ellipse. And so those constraints that make us stick only to ellipses may be written as equations that say such and such a relation between one boundary point and another has to have this particular relation. And then we're going to be interested in optimizing over all possible parameters that satisfy the constraints. And so we'll have constraint-based optimizations. And that's done using a method called Lagrange multipliers. You probably saw the general idea of Lagrange multipliers in your calculus course, but you probably forgot. We will come back to it, and especially because we're going to be dealing with situations with many constraints, we will be understanding how to do optimizations with many constraints. In past times I've offered this course, I have not got to this bracketed stuff, but if we have extra time, there's optimization when the variables you're optimizing over don't appear linearly in the so-called objective function, the function that you're trying to maximize or minimize. And if we had time, we could talk about that nonlinear one, Levenberg-Marquardt. And it turns out information theory and the notions of entropy and mutual information are also pretty important within image analysis. And if we have time, we could talk about that. Any questions about the topics in the course? Okay, Niazi.
Thank you, Professor. As an undergraduate, I'm just wondering, during the course, will we have the opportunity to both practice these methods and apply them, or are we expected to come in with sufficient comfort in the methods so we can directly apply them?
I will be talking about the methods. I will be talking about the underlying mathematics that is not assumed. I expect you to know what a directional derivative, but I will certainly be reminding you what one is, and I will be talking about how to compute it. And then you will have homework in which you will be computing it. Does that sort of answer your question?
Thank you. Yes, it does, and it puts me at comfort.
Good. I mean, put another way, I take the prerequisites seriously, both in the positive and negative sense. In the positive sense, I expect you to be solid on the prerequisites. In the negative sense, I don't expect you to be solid on anything that's not in the prerequisites. Okay, this is what I said last time. It's on the information sheet. You have to come to class. You have to do the assigned readings such that they are, and especially you have to be prepared with these lecture notes. In terms of office hours, this week they will be remote, but I intend next week, assuming that I'm teaching in person, the office hours will also be available in person. If you need for me, if for whatever reason you need to meet with me at office hour time, but remotely, you send me email and I can set that up at this, so that we do it via the Zoom site. It works much better if you do it in person. My office is the northeast corner of Citterson Hall. Be aware that the door from the corridor says 221 Citterson. My office is off of 221. It was originally set up as a secretary's office, if you will. But anyway, the upshot is that I'm in 222, which is off of 221. I already talked about the Piazza site. I already talked about homework. I want to talk about lates on homeworks. Homeworks will have a due date. If you pass the homework in on time, you will be able to get 100% of the available credit. For the next week, you will only be able to get 90% of the credit. That is to say, if there are 100 points on the available on the assignment, and you would have gotten an 80%, you would instead get a 72%. Yeah, understand? 90% of whatever score you earn. And more than 1 week late, it will be docked 50%. However, with regard to the slightly late ones, the ones that are passed in late but within the first week, I will give you a free one of those. So if you say, you come to me and you say, geez, I have a special exam this week, I need to be late. Well, then you use your free late, right? So that's the whole point. Hopefully you won't have any late ones, but if you are late within a week, the one whose score, the one for which the docking would be the greatest, will not be docked at all. Okay. The second, all the rest of them will, if you have more than one late, one slightly late, one late by no more than a week, then those would be docked the 10%. There's no free 50% lates. These assignments are really important to the learning in the course, and having them done on time means you'll be able to understand the upcoming lectures. That part of the learning of the material. It'll make you understand it better, and make you understand what you don't understand. Okay, any questions? Okay, then I am going to move on to the next slide set, which is in the actual beginning the first topic in the course. So let me, first of all, stop the share. And let me get at my file of lectures and move on to a new slide set. Hope that's not the one I wanted. This is the one I wanted. Okay, good. Okay, so the way I've got these set up, I repeat the slides that you've seen, and I put in bold what we're going to be talking about. So this topic that we're going to be talking about is representation of images in Taylor series and computation of image derivatives. Okay, and for that, well, I'm not sure I screen shared, so let me get it so that I do. Yeah, I didn't. Someone should already have hollered at me. Wait a second, I don't see what you're talking about. But anyway, here we go. Can you now see the slide on the screen?
Yep.
Okay, so this bold thing is what we're talking about. And moving on. If you have an image like you see in the upper left, it's lighter in the left half of the image and darker in the right half of the image. That is to say that the pixel intensities are higher on the left and less high on the right. If you consider that as a function of a continuous variables x and y, and you take the first derivative with respect to x, what you will see is that as you go from left to right, the value of the first derivative in respect to x will be 0 because there's no change in the intensity. And then it will be a big negative number right here where it drops to a much lower value, and then it'll be 0 again. So the derivative value would be 0, 0, 0, very, very large magnitude negative number 0, 0, 0 as you go across any one of these rows. Okay, so that's the first. And if we square that, what you will see that you get zeros and then a very high value. And so the image, the value of this derivative image at each one of these pixels will be 0 in most of the image, except very high, very bright at this place, which is the edge between the high intensity patch and the low intensity patch. Anyone doesn't see that, ask a question. The same thing goes for this next image that we have in the second row, except we're going to take the derivative with respect to y because the variation is along y. And so now we're taking the partial derivative of the image with respect to y and squaring it. And what we will get is, again, zeros in this region where along y things are constant, and high value along this line, which is the edge, where you have high contrast. Okay, so we're already seeing that these derivative squared values can yield where the edge is. But of course, it depends on the orientation of the edge. So if I look at an image that's inside this square, the part of this bigger intensity pattern that we see here, if we took our derivatives orthogonal to the edge and squared them, so in other words, I'm needing to determine a direction given by a unit vector u that is in this direction, this sort of diagonal direction. And if I took that directional derivative, talking about rate of change along that direction, what we would see is you have high contrast here, corresponding to a negative derivative, which squared gives you a high value, and then zero values. And then here, the derivative would be highly positive, right? Going from a small intensity to a larger intensity. And so the resulting image would look like we see here with two bright line segments, everything pretty much zero everywhere else. And we'll be able to say that we have edges here and here. So the point is that derivatives are, first derivatives and directional derivatives are going to be important as we want to find edges of things. Notice that basically we're going to have to, in the bottom situation, not only figure out where the gradient magnitude is high, but for which values u it's particularly high, for which orientations. Orientation is determined by a single angle called theta, but we'll be thinking of it in terms of unit vector u in that orientation. Any questions about how derivatives and edges are going to be related? Okay, now if we have bars in images, okay, so if we look at the top left input image, it's now not light on one side and dark on the other, but it's dark along the bar and along this vertical bar and zero otherwise. What we could think of trying to find its left edge and right edge by the first derivative method, but we could try to find the whole bar by a second derivative method. And so if we take the second derivative, second partial derivative twice in x and square it, because we don't care about its intensity, we will find that the center of the bar gives a particularly high value. And so that this image on the right of second derivatives twice in the x direction, okay, will yield the center of the bar as this bright bar. It'll fall off a little bit along the bar and eventually turn to zero as we get outside. Likewise, for a horizontal bar, we'll want to take the second derivative image squared twice in the vertical direction, twice with respect to y. And we can look at the same thing in any direction we want. And so we have this notion of a second derivative twice in some u direction. I will notate that with a big D, meaning derivative, super 2. If super 1 will mean it's a first derivative, super k will mean it's a kth derivative, super 2 means it's a second derivative. And when it's twice in the u direction, I will call it d2uu of that image. Notice that this d2 of I dx squared twice in the x direction corresponds to a u in the unit vector in the x direction, which we sometimes notate as little e sub x. So another way of writing the second derivative twice in the x direction, one way is this partial derivative, but we can also write it as d super 2 sub e sub x of I of xy. Notice that sometimes we're going to be interested in mixed partial derivatives. So for example, d2 of I by dx by dy, in which case we will notate that as d super 2 e sub x e sub y of I. Okay, so the two directions. One way of understanding a second derivative is that it's a first derivative of the first derivative. The first partial derivative will be in one direction u, the second one in some direction v, in which case it would be d2 sub u v of I. And for us, the ones we're going to be interested in, especially, are twice in the same direction. So it's going to be d2 sub u for some derivative direction u, where this is a direction in the image. Questions about that? Okay,
So with this
Go
method,
ahead.
I'm sorry. So with this method, you can only find the center of the bar. Can you find like the width of the bar?
Extremely good question. And the answer is yes. And we will talk about that, but that has to do with the aperture question that we said we're going to deal with. It turns out that there will be an optimal aperture, and the aperture that we want to use will determine the width. I love that creative idea. Any other?
Thank you.
Okay.
One quick question, sorry. This is Millie. Why is there a power of 2 outside of the brackets?
Well, that's because we want to get, if we only wanted dark bars, we'd want one, we would want one sign without the square. Or if we only wanted light, one would be a very high second derivative, the other would be a very high high magnitude negative one. But if we want to look at both dark bars and white bars, we use the square so we can get either light bars or dark bars relative to the background. Clear?
Yes, thank you.
Okay, so now we consider this gradient thing. First of all, the gradient of an image, the gradient value at any point, is gotten by taking the first derivative in the x direction and the first derivative in the y direction, and considering that as a vector, as a tuple. Okay, so we have d by dx of I in the first entry and d by dy of I at the second entry for any position xy. And if we want to know the direction in which that gradient is maximal, we can look at the unit vector, which is di by dx. Let me put on the camera because I want to write on the screen here. So hold on, let's share screen. Let's go advanced. Let's put on the camera. All right. So I have this vector, which is called gradient of I at xy. And it has two entries. And the first entry is di by dx at xy. And the second entry is di by dy at xy. Okay, so that is a vector. And if we divide that by its magnitude, which is di by dx at xy squared plus di by dy, we take the square, the sum of the square of the entries, and we take the square root. So now we have the gradient divided by its magnitude, and that's a unit vector. And that unit vector, which I will notate as gradient with a hat on it of I, hat means it's unitized. It turns out that that direction is the direction such that the directional derivative in the u direction is maximal. So it yields the u. If you take these two derivatives, one in the x and one in the y, it yields an optimal direction u in which to take the directional derivative. Put another way, the actual magnitude, which is di by dx, is what this denominator is the magnitude. This guy in the denominator can be written as grad I of x, y magnitude. Okay, square root of the sum of the squares. That magnitude will be the directional derivative in the optimal direction. That's the u that we want. And the result is that gradient magnitude is a good kind of image, to produce an image of gradient magnitudes is a good edge strength image, gradient magnitude image. Okay, so far so good. Any questions about that? Well, it turns out that there is a more general way of thinking about second derivatives too. So now we're going to be interested in not just d1 of I, but this d2 of I thing. All right. The second derivative. And instead of a vector, the second derivative operator yields a 2 by 2 array in 2 dimensions, or a 3 by 3 array in 3 dimensions. And up here is d2 ex of I. And down here is d2 ex ey of I. Whoop, let me get that on the screen. And in the corners, because the mixed derivative is symmetric, in both of those places, there will be d2 ex ey of I. That is to say, the second partial derivative once in the x direction and once in the y direction. This matrix, which is called by mathematicians the Hessian of this function I, is useful in forming directional second derivatives. We will see that once you have the gradient, you can find any directional derivative by simply dot producting this gradient thing without the denominator, by dot producting it with the vector u. So to get the directional derivative in x, that is to say, to get d1 with respect to some u direction of I, we will be taking this grad of I thing and dot prodding it with u1, u2, where u1 and u2 are the coordinates in xy of the u vector, of the unit u vector. So you can think of the gradient operator as a tool that allows you to compute any directional derivative by simply dot producting it against the u vector. Questions? Back to the Hessian, the second derivative, so-called tensor, it's a matrix here. It turns out if you want to get the second derivative twice in some direction u, you will multiply this matrix by the u vector, the u1, u2. And that'll give you a vector, and then you'll dot product that vector with u again. Okay, so if you will, you want to think of producing a u on the left and a u on the right. So we have u1, u2 here, and u1, u2 here. And if we do that operation, that will have produced this second derivative directionally twice in the u direction. And if we want to go a mixed u and v, then we'll have uv here, and this will be v1, v2. It's another vector. Okay? So the point is the Hessian is also a tool for getting any directional second derivatives, mixed or otherwise. You simply can multiply by these vectors and you'll get those second derivatives. Questions on any of that?
What was
Okay.
the original letters at the bottom of those terms, like D2 and then EX and what Y?
EX, EY. So it's another, the EX vector is the horizontal unit vector, and the EY vector is the vertical unit vector. Put another way, in coordinates, EX is 1, 0, and EY is 0, 1.
Okay, thank you.
Okay, so let us get back to the slides. I'm trying to share screen. I hit the wrong button. Thank you for correcting me. So I'm sorry, the recording will be missing a little bit, a minute of the proper recording. Thank you for catching that. Okay, so let's get the camera. You can see why the whiteboard would be so much better to work with. Any case, if you, in 3 dimensions, if you consider the Laplacian of I will be d2i by dx squared plus d2i by dy squared plus d2i by dz squared. And in n dimensions, you just take all the so-called cardinal direction second derivatives. So, okay, so, and in 2 dimensions, it's just without the d2i by dz squared. It turns out that the Laplacian result squared is particularly sensitive to circular blobs, little tiny circular blobs. So if I stop sharing and get back to my share screen, and if I have an image with a little circular blob, and I take the Laplacian at every image position, then everywhere where the image is constant, it'll produce 0, and it'll produce a high value here in the result, 0 everywhere except high value within the blob, basically at the center of the blob. Okay, so we now we have found ourselves edge operators by first derivatives, bar operators by second derivatives that are oriented, and circular blob detectors, if you will. I should have operators, I should have said detectors, which are circular ones that are, detectors of circular blobs via the square of the Laplacian. I will note, by the way, that all of these results are independent. The gradient magnitude is the same no matter what your x and y directions are, or in 3 dimensions, x, y, and z, in which case you would have 3 entries in the gradient vector, di by dx, di by dy, and di by dz. But any orthogonal group of directions will do. It can be x, y, or it can be u and it's perpendicular. It all works. And the same thing about the Laplacian. The Laplacian value does not vary depending on what your coordinate system is, as long as it's a unit so-called frame, a set of coordinates. Okay? Okay, so we've already seen then that first and second derivatives are particularly important in finding edges and bars. We'll later see that we're going to be interested also in some third derivatives and fourth and maybe even fifth derivatives. And so we need to understand the generalization of this notion that if you have a gradient vector, you can get any any directional first derivative. We've seen that in 2 dimensions, we have another operator, which is a matrix, which will allow us to get even mixed or unmixed any second derivatives. We're going to find out that there's a similar operator that in three dimensions that will give us all possible third directional derivatives, mixed or otherwise. Likewise, there's going to be one for fourth, and for any k, there is going to be an entity, an array, in fact, which will allow us to compute those derivatives. And those entities are called tensors, okay? And they are operators that apply linearly as in weighted sums, the way dot products do in 1 dimension, the way matrix multiplication works in 2 dimensions, and so on. We're very careful. There's two different dimensions that we're talking about here. The dimensionality of the space, which I'm going to call n, and the degree of the derivative, which I'm going to call k. Okay, and these are, okay, so let me be careful. Okay, so here comes a nasty slide. Lots of things on it, and we want to talk about it. Okay, so we're gonna refer to yes, we're going to talk about these vectors, these array, well, more precisely, the representation of vectors as tuples. And these vectors are going to have n entries, 1 per dimension, like the gradient, right? We had the first derivative with respect to the first dimension, then the first derivative with respect to the second dimension, and so on, up to the first derivative in the kth direction. Sorry, boy, did I mess that up. The first derivative we get to the nth dimension. So if n equals 2, you have 2 entries. If n equals 3, you have 3 entries, and so on. The first order tensor is a column vector. It's an n by 1 array, right? N rows, 1 column. The second order tensor is going to be an n by n array. It's a matrix. We're used to that. The third order tensor is now going to be an n by n by n array. It is an array, the array itself at any position, the values there at any xy, at any xyz, or at any xy position, even if you're in 2 dimensions, it's going to be a 2 by 2 by 2 array. It's going to have 8 entries, right? It's going to have rows, it's going to have columns, and it's going to have a variation in depth. Okay, so these tensors are a generalization of the linear entities, the things that are applied linearly that you're used to. A 1 tensor is going to be n by 1. A 2 tensor is going to be n by n. A 3 tensor is going to be n by n by n. A 4 tensor is going to be n by n by n by n. Okay? Okay, so what we have seen so far is that the gradient is a 1 tensor, a first order tensor. It's a 1 tensor with 2 entries in it. If you're in 2 dimensions of space, if the image is 2 dimensional, it's a one tensor with 3 entries if you're in 3-dimensional space. It's a one tensor with 4 entries if you're in 4 dimensions of space, for example, XYZ time, and so on, right? You can talk about the order of the tensor, K, and the dimension of the space, N, as separate things, and it's really important not to get confused by one. And so the idea is that in a K tensor of an image F, or I've been calling it I before, you're going to have n to the K entries. And each of them is going to have a kth derivative in that slot. So for the one tensor, you had a first derivative with respect to x and a first derivative with respect to y. In the Hessian, you had the second derivative with respect to xx, the second derivative with respect to yy, and the second derivative with respect to xy, and the one with respect to yx. Of course, the xy one and the yx one are the same values. Notice that's all combinations of 2 entries in the derivative. One of them is the direction of the first, like x, and the other is the direction of the second, which may also be x. So the upper left entry is d2i by dx squared, by dx by dx. The lower right entry of that matrix is d2i by dy by dy. The upper right entry is once in x and once in y. It's d2i by dx by dy. And the other one is d2i by dy by dx. And so all combinations of the first direction you're taking derivative with respect to and of the second in that Hessian are going to be the entries. And the same thing is going to go for the 3 tensor. So in the 3 tensor, you're taking third derivatives. There are 3 possible directions in the subscript, x, y, and z, and you're going to have xxx. In the upper left, you're going to have YYY, and the next one down in the diagonal of the 3 tensor, and ZZZ, and you're going to have XXY and XYX and XYX and YYX and so on and so forth, all the different 9 possibilities of places that where the directional derivative is specified. I will get that much clearer by example on Tuesday, but I've run out of time for today. Are there closing questions? If not, please remember that you are to receive an email by noon on Monday as to whether the class on Tuesday will be remote or whether it will be in FB 007. I'm hoping it will be in person, but I fear it will be remote. In any case, you should receive that email, and if you don't, send me an email asking where the class is. Okay. Till next time.
Professor. So the K tensor is like it's like the Hessian matrix, but extrapolated for as many dimensions as you need.
Okay, I'm going to close the session.
Professor, will the exercise at the end of the slide still be due on Tuesday?
Yeah.
Okay, thank you.